All right, guys. So now we're going to talk about power transmission and transformers. So generally, in the beginning of 20th century, there was a tug of war between AC circuits and DC circuits, and it was basically Tesla versus Eddington to which one will win to, let's say, be able to supply cities with electricity. Um, the Edison was for the DC circuits, um, Tesla was for the AC circuits, and both of them were basically in competition with one another. The difference between them was that um, for the Edison, in order to provide DC power to the residential area, he had to have a sort of like a power station at every block. Where for the AC circuit, then the main power station could be, let's say, outside of the cities, and then all the electricity can be, transferred basically using those lines, like electric lines and things like that. And eventually, it appeared to be, more financially and economically, more, let's say, better than Edison's, DC circuit, let's say, a project. So all the cities went with the AC circuit, and that definitely makes much more sense. That means what we have here is, let's say, this is your city. The main stations would be somewhere outside of the city, where then what you have, some kind of like generational electricity. Could be, in terms of, like, let's say, a nuclear power plant, or maybe some kind of, the water power plant, or some kind of, the wind turbine, something that, gathers and gathers energy, electricity, and then it uses, basically the transmission lines, and the electricity through those lines. Basically, it's a, the voltage difference, some kind of voltage, and there's a current, and generally, the large voltage is actually relatively safer than the large current. So that's why most of those, power lines come with extremely high voltage, which basically minimizes the loss, in transmissions. And some of those lines can be as high as, 350, kilowatts, which means like 350,000 watts. Sorry, volts, 350,000 volts of voltage. Some can be as high as, like, let's say, 700 or 800,000 volts. But the idea here is that, this is basically all done pretty much outside of the city. And then when you have those, when you get to the city, then you have more, smaller sort of, like, let's say, distribution stations. And from that, the lines then decrease the voltage from hundreds of thousands to roughly 20,000. And so let's say, and then it goes to the residential, let's say, blocks, right? So and every block has even smaller stations, but such that the lines over there, not necessarily stations, but more of a, something like this, right? So you have a, so, like, let's say, in the residential area, you have those lines basically coming into some kind of this a transformer. This is actually what we have for as a transformer. And then, let's say those lines become even less, about 4,000. And sort of like, let's say, each small neighborhood has several of this type of transformers where 4,000 volts comes in, and then it distributes to, several houses. And this 4,000 volts basically converts or transfers, into this, into the houses as 120 volts or 240 volts, depending, what it is. But the idea here is that in terms of the AC, let's say, distribution of electricity, it's much more efficient, and it also much more economical. So that's why it's eventually, uh, everything pretty much uses AC circuits. All right, so in terms of then what we have here is this transformer is pretty much what it does is takes, let's say, those a very high voltage, right? As I said, right? So let's say right before it enters anybody's house, you have a transformer like this that converts, or takes in, high voltage and gives low voltage as the output. That means, for example, 4,000 comes in, and then the one that goes into the houses are basically, 120 or 240 or something like that. And the way we can, let's say then take in large voltage and basically output as a low voltage is pretty much done by transformers. So let's look at in terms of what is a transformer, how does it operate, and the next few slides basically gonna pretty much give us, like let's say in terms of the operation of the this device that we call a transformer. All right, so generally what we have here for a transformer. Okay, so what we have here, we have two coils. One is a primary, the other one is secondary. So here we have a primary, and you wrap it around, some kind of, iron core, and it's connected to an AC generator, right? Function generator, and it can have then N. Let's say NP, which is number of turns for the primary. If you want, you can just basically also use N1 as a coil one. So N1 is the number of turns in coil one. Okay, so let's do that. So N1 is the number of turns in coil one. Delta V1 is the voltage, alternating voltage supplied to that coil one by the function generator. And on the other side, we have another coil that is not connected to any power source, but it is basically wrapped around the same let's say iron core, and it's connected to some kind of resistive load. Okay, so this is then what we call secondary coil. Primary is basically where we get our input, and then the secondary is where we have our output. In a way, one of those let's say for those typical transformer in residential area, 4,000 volt will be the input voltage, and then 120 will be then output voltage. And what's happening inside, let's say then the voltage is basically large amount of voltage is taken in, and then a small amount of voltage is given out. So let's say how it's possible. And it's extremely simple device in a way. Like let's say you're going to see that even the equation that we're going to be using is relatively straightforward. But one thing we have is that it basically works like since the voltage is varying in the coil one, that means it has a current in coil one, and which basically generates a magnetic field, which can then travel, let's say like this, right? And that means now there is a magnetic field inside coil two. And if the voltage and current varies in coil one, then that means the magnetic field varies through the coil two, which then induces current and EMF, as we already have learned. That means what we have here is, in terms of primary coil, again, so it's connected to alternating voltage source. It's, it doesn't work if it's a DC source. Transformers, specifically designed to work with the, AC circuits, right? Because the current through the coil two, or current through the coil one has to be a varying current, so that the magnetic field or the magnetic flux through the coil two changes with time. That means only when this magnetic field changes with time, then we will have a, obviously induced EMF. Okay. So then in terms of what we have here is the reason we use this iron core, because it increases the magnetic flux through the coil, provides medium in which nearly all magnetic field lines through one coil pass through the other coil, and also increases mutual induction of the coil. As we learned, right? Remember, mutual inductance is we have two coils near one another. So technically what we have here is it uses the concept of mutual inductance, and you don't really need an iron core for the mutual inductance, but it makes it better. You can see that the advantage of iron core: increase the magnetic flux, provide the medium through which the magnetic field are moving through, and also increases the mutual inductance of the coils. Now, once we have that, then we can look at it in terms of the delta V, right? Potential difference for the coil one. And this is, remember, so basically what we have here is as soon as there is a induced, let's say, induced magnetic field, as by the coil two, right? That means, remember, it induces EMF, current, and induces magnetic field. So then it tries to oppose the change in magnetic field directed by the primary coil. And then, basically it also then generates its own magnetic field that, coil 1 then affected by that. Then delta V1 is equals to negative N1 change in magnetic flux divided by dt, right? The change in flux over time, where the flux is the magnetic flux through each turn, and N1 represents number of turns in coil 1. All right, so we can assume that all the magnetic field remain within the iron core, and flux through each turn of primary coil is equal to the flux through each turn of the secondary coil. That means, the flux is exactly the same for both coils. That means if I write down delta V2, this will be negative N2 change in flux over time. Okay. So which means that if I have then the flux is the same for both of them, then I can, rearrange things like this. If I do a ratio of equation 1 divided by equation 2, then change in flux over time can cancel out. Then I have delta V1 divided by delta V2 is equals to basically N2 over N1, N1 over N2. Okay, so the negatives also cancel out. So I have N1 over N2. Then from here, we can rearrange and basically solve for the delta V2, which is the output voltage. So you can say like delta V2, then it's going to be N2 divided by N1 times delta V1. And this equation is, the simple equation that basically allows us to pretty much take in some voltage as an input, then give you as an output voltage. And the only thing that technically then matters is just a difference in terms of number of turns. See, if the N1 is equals to N2, that means both coils have exactly the same number of turns, then that ratio is 1. Delta V2 is equals to delta V1. That means output voltage same as input voltage. But if I have much larger or much lower, let's say number of turns in coil 2 relative to coil 1, then I have a completely different output voltage. Remember, the transformer doesn't just take large voltage and gives you a low voltage. It can also take a low voltage and give you a large voltage. So you can see, right? So for example, if you have 100 times more, let's say N2 is equals to 100 times N1. All right, so let's say you have a 3 over here and 300 in the other one. So you can say 100 N1 over N1 times delta V2, delta V1. You cancel those, then output voltage is 100 times more than input voltage. And if the number of turns is basically less, then the output voltage will be less than the input voltage. All right, so again, delta V1, delta V2, then take the ratio, delta V1 over delta V2, by understanding that the flux is the same for both of them, so changing flux is the same for both of them, we arrive the equation for the basically transformers. Okay. Now from here we can see that this transformer basically gives you the how to calculate the output voltage from the input voltage, and all you have to do is just look at in terms of what your number of turns difference. Okay. So here's again, so like let's say the diagram for this, and what we can see here is that N1 and N2 basically pretty much determine what we have. So delta V1 is equals to N2 over N1 delta V1, sorry, delta V2. That means we're looking at output voltage. So let's see what we have. So let's say if, as I said, right, if N1 is greater than N2, so let's say N1 is greater than N2. In this case, what we end up with is, that means, number of turns in the secondary coil is larger than number of turns in the primary coil, just like I said, right? For example, 100 N1 over, N1, delta V1. Here we can see that delta V2 is greater than delta V1. Okay, so that means what we get here is we get larger output voltage. So this is known as a step-up transformer. So this is step-up transformer. So step up transformer is when N1 greater than N2. Okay. Sorry, actually N1 less than N2 greater than N1. Sorry, guys. So if N2 is greater than N1, so then you get step up transformer, which means that the output voltage is larger than the input voltage. And what you can see is that greater the difference between number of turns, let's say greater the N2 relative to N1, more output voltage you will get. Then what we have here is, let's say we have okay, so let's take then when N1 is greater than N2. So what we have over here, well, in that case, delta V2 is equals to N2 over N1 times, let's say, delta V1. So for example, you have N1 is equals to 100, N2 is equals to 10. Okay. Then what we get here, we get then 10 over 100 times delta V1. That means from here, what you get here is you get then 1/10 times delta V1, which means that delta V2 is 10th of, delta V1. That means secondary or output voltage is only 10th of, a primary voltage. And that's what we have for the, household, like transformers, right? Those transformers take, 4,000 and gives you 120. That means they take large voltage and give you a low voltage as output, which means that, N1 is much larger than N2. So then you can get, much smaller, output voltage. All right, so here's, you can see an example of a transformer. You can the primary winding in the transformer is attached to the prongs of the plug. So this is basically what you have in the household, right? Whereas the secondary winding is connected to the power cord on the right. Okay, so what we get here is, so this is basically the power, where the one thing that those two have, by two means like primary and secondary, let's say coils, is not only the flux is exactly the same through each coil, also the power is exactly the same for each coil. That means I can say that power 1 is equals to power 2. And power, remember, is current times voltage. So the product of current times voltage for power 1 is same as product of current times voltage for power 2. I mean, for the coil 2. Then from here, we can look at how we can rearrange this. So remember, so then I1 is equals to delta, delta V2 divided by the resistance. And this is the load resistor. All right, so one thing I would like to mention for this slide, when N1 is greater than N2, this is known as a step down transformer. So step up and step down transformers. Step up is when you're increasing output voltage. Step down is when you're decreasing the output voltage. All right, so here then remember, so as I said also that power is the same for each coil. Then what we have here is, because then you have the current in the primary coil, and whenever it changes, there's then induced current in the secondary coil. And in this equation for the power, we are using capital I and capital delta V, and those are basically RMS values. Remember, root mean square values, right? So generally when we're talking about, time varying values, we use a lowercase, but this is basically the RMS values. And remember the second coil was connected to the resistor. So if load in the secondary circuit is pure resistance, then induced current in phase with induced voltage, because we talked about, right? So whenever you have a resistor connected to to your circuit, only resistor, then current and voltage are in phase. And in this case, induced current is in phase with induced voltage. That's for the, a secondary, right? So let's say secondary coil. So here's a secondary coil connected to a resistor, and everything induced over here, right, is basically induced voltage and induced EMF, induced voltage and induced EMF are in phase. Okay, then the power that we have here for circuit one and circuit two, or coil one and coil two, this is supplied to secondary circuit. Basically, must be added, must be provided by AC source connected to the primary circuit. Okay, so in an ideal transformer, and this is basically ideal transformer where we assume that there is no energy loss to to environment. So the power I1 times delta V1 supplied by source is basically same as power provided to the secondary secondary circuit. And uh, the value of load resistance, this RL, is then determines value of the secondary current in this in the circuit. Because remember, so how much a current we will have always depends on the voltage, which is basically, this is the induced EMF. This delta V2 is the induced EMF, but also because there's a resistor connected, which acts like a controller for the current. So then we have a delta V over RL. Okay. So then the current in the primary, in the primary coil will be given in terms of delta V1 over R, equivalent. So where equivalent resistance of load resistance when viewed from the primary side. Okay. So, and the equivalent resistance and load resistance, they're not the same if the number of turns are different, because the way equivalent resistance related to the load resistance is basically given with this equation, where you have N1 over N2 square times then the load resistance. That means only when N1 and N2 are the same, then you have equal, resistance equals to the load resistance, but then you can have that to be larger or smaller, depending on the difference of the number of turns. All right, so relatively, straightforward way of looking at those all those things. One last, I guess, additional equation that I can give you is this. So coming back to the equation of the power of the primary equals the power of the secondary, you can see that if I write down I1 times delta V1 equals I2 times delta V2, then what I can do here is for the delta V2, I can write down this equation where that we just showed, last slide. So delta V2 is equals to N2 over N1 times delta V1. This also can be in terms of even RMS values. So here, if I replace then I2 times for the delta V2, I write this N2 over N1 times delta V1. Then I can cancel this delta V1 and I can write down I1 is equals to then I2 times N2 over N1, or basically have equivalent equation for the current 2, which will be then N1 over N2 times current 1. That means one thing we will see here is for the current is going to be the opposite. Whenever you have a step up transformer and the voltage output will be larger than the input voltage, the current actually will be less than the in the primary compared to the the current will be less in the secondary compared to the primary. So when you have a step down transformer where the voltage output is less than input voltage, then the output current will be greater than an input current. That means, you can see right here, the ratio is instead of N1 over N2 over N1 is N1 over N2. So you can see, right, comparing to this two equations, you can see, right, for the voltage is N2 over N1, for the current is N1 over N2. That means whenever delta V2 is increasing, I2 is decreasing the output, relative to the input. All right, so let's then look at some examples here. A neon sign transformer has a 450 watt AC output with RMS voltage of 15 kilovolt when connected to a normal household outlet. There are 500 turns of wire in a primary coil. Okay, so how many turns of wire does the secondary coil have? Okay, so then one thing we can say here is, V2 over V1 is equals to basically N2 over N1, or V2 is equals to, well, here, we're looking for the number of turns in the secondary coil, so N2. Then N2 is equals to V2 over V1 times N1. Okay. Now, we are told that V2 um, is the output, right? Our output, our RMS voltage is 15 kilovolt. Okay. So this is basically V2, so 15,000 volts. Divided by V1. So what is V1? Well, V1 is basically this transformer connected to the household outlet. Well, household outlet has a, the, you know, let's say transformer connected to household outlet will have an input of 120 volts. Okay. Then times N1, when N1 is the primary, right? So we have 500 turns. We calculate this and we're going to get 62,500 turns. Okay, so roughly 63,000, turns in the secondary. So that's why, because then, you can see, right, N2 is greater than N1, right? So as we talked about, right, when N2 is greater than N1, you have a step up transformer. So step up transformer then increases the output voltage. It went from 120 to a 15,000. So it's kind of like opposite what you get into your household. All right, so then part B says, when the transformer is running full power, what is the current in the secondary coil? What is the current in the primary coil? All right, so then here what we can do is use the equation for the power, because we're not given anything about resistive load. So, but we have the equation, here we have the power, 450 watts. Remember, P1 is 450 watt, but so is P2. That means P1 is equals to I1 times V1. So then from here, I can say then I1 is equals to P1 over V1. So this so it's 450 watts divided by 120. This is 120. This is basically looking at the primary coil first, volts, right? So this will give us then 3.8 amps, roughly. Okay. Then if I use P2 is equals to V2 times I2, then I2 is equals to P2 over V2. So 450 watts divided by 15,000 volts, right? So then this will give me then a 0.03 amps. So I2 is roughly 30 milliamps. So that's basically how we can then calculate this. Or, equivalently, we could have just said, once I calculated I1, I could have said then, I2 is equals to N1 over N2 times, I1. But I needed to know this value, let's say, so that I can calculate the second one. I could not use this first, this equation from the beginning because I had two unknowns. I1 and I2 were unknown. All right, so here's one more example. So unit transformer that will draw 15 watt of power from a 220 volts RMS power line, stepping the voltage down to 6 volts RMS. What will be the current in the secondary coil? What will be the resistance of the secondary circuit? And what will be the equivalent resistance of the input circuit? All right, so let's see what we have. So we're given power, 15 watts. Remember, P1 is equals to P2. It's always going to be true. Then we're given that we'll draw from 220 volts. That's my V1. And then output is just 6 volts. Okay, 6 volts. And using the RMS values. So it says, what will be the current in the secondary coil? Well, secondary coil, that means it's I2, which I can use then P2 divided by V2, as we already looked at in the previous example. So this will be 50 watts divided by V2 is 6 volts. So we get 2.5 amps. Okay, so this is basically part A. Part B says, what should be the resistance of the secondary coil? Okay. Now, Secondary coil resistance is, remember, is always a ratio of voltage and current. So R2 is equals to V2 over I2. Well, I have V2, 6 volts, and I2, 2.5 amps. Well, this will give me 2.4 ohms as a resistance. Okay. And finally, the last part, it says, what will be the equivalent resistance of the input circuit? Well, so from here, there are a number of things we can, let's say do. And one equation that we had was this R equivalent is equals to N1 over N2 square times then the load resistance, which is basically, R2 in this case. Now, I do not have number of turns in this case, right? So I don't know what, N1 and N2 are. But one thing we can do here is, let's say, I don't know what separately N1 is, what separately N2 is, but remember, I have my V1 and I have my V2. And remember, the equation was in terms of the V1 was equals to, or V2, right? We should have V2 equals N2 over N1 V1. So we had this equation for the output voltage. See, if I rearrange it, right, let's say cross multiply, then what I can say here is that V1 and V2, kind of move them around. Same thing with the ratio of N1 and N2. So then N1 over N2, because that's basically what I have here in this ratio, right, is N1 over N2. Okay. Since I have N1 over N2, so I can just basically rearrange this so that I have N1 over N2. And that basically will be V1 over V2, right? So V1 over V2. Then if I calculate this, then what I will get here is, so V1 over V2, V1 is 220, V2 is 6. So it will be 220 divided by 6. Okay, so I'm going to get 36.7. It's unitless because volts cancel out. Okay, then when I come back then to this equation, I can say then, all right, so R equivalent is equals to N1 over N2. Well, I don't know again what N1 and N2 are, but I know what the ratio is, 36.7. So 36.7 square, then times 2.4 ohms. Then I can basically calculate this and get, well, roughly 3,300. So 3,300 ohms. There you go. So roughly 3,300 ohms. Okay. That means, again, we don't know what, N1 is individual, N2 is individual, but we can always find out what the ratio is if you're given the voltage 1 and 2. All right, guys. So that's it for this chapter.